Hello, everybody. Welcome to the course of First Steps into Model Order Reduction. Steps into Model Order Reduction. So my name is Alessandro Alla. I'm from the math department of PUC-Rio. If you wanna contact me, my email address is alla@math.pucibrio.br, and if you want to know more about myself, you can visit my website, Alessandro Alla.com. All right. So really feel free to contact me anytime. Especially, I mean, this is I don't know, a bit a weird way to do online teaching, in my opinion. But really feel free to contact me anytime after that you watch those videos, or when the first week of August I will be online to try to do some to reply to some questions and to give some more details. The outline of these 5 lectures, those are going to be 5 lectures. I will basically follow I will basically follow the notes that I wrote. So I will start giving some motivation. So let's say why model order reduction. From now on, I'm going to call us MORE, which stands for model order reduction. Is important. Then I will recall, I would say, finite difference method. For PDEs, partial differential equations. I will talk about singular value decomposition. And proper orthogonal decomposition. I will discuss the discrete empirical interpolation method. And actually, if there is time, I will show some coding. By the way, the lecture note will closely follow these lectures, And also inside the lecture notes, you will find piece of coding. So that should be quite straightforward to try to use model reduction, at least for the example that I provided in the PDF in the notes. I would say that it's very good to already have a knowledge about PDEs, about discretization of PDEs. Here, I just recall find difference method, but could be any discretized method to approximate any method to approximate partial differential equations. Knowledge of a singular value decomposition is okay, but I will basically recall the main features of this method, and also knowledge of MATLAB or any other software to implement some algorithms. I believe it's important. All right. Let's see. First of all, I want to give some motivation. So let's suppose to have a diffusion process in a domain. And this domain depends from some parameters. So it's a parameter dependent domain. So the problem that I have in mind is something like minus divergence, a coefficient which depends from mu grad y equal f in a domain omega. And then I have, for instance, Dirichlet zero boundary conditions on gamma, which is the border of omega. This is my problem that I call star. And for instance, my coefficient A of mu might be given, for instance, by two parameters, D1 if X is in R, in the region R that I'm going to draw, and D2 if this is in X in omega minus R. And for instance, I can imagine that this is omega and this is R. So essentially I have a diffusion process where I have a parameter D1 inside this rectangle, and I have a parameter D2 outside the rectangle R. So I have a parameter space that I call, for instance, mu, which is given by mu1, mu2 with for instance, they are positive. And they are bounded. Okay, what is the goal? Is to find so what we want to do, we want to solve this problem for many parameters, for many different parameters. So therefore, the goal is to find a surrogate model of the form A tilde y equal f in omega and y equals 0 in gamma. That represents our original problem, star, sufficiently well. Over the whole parameter domain. So what does it mean? What does it mean? So here we have an infinite dimensional problem, okay? That depends from some parameter, in this case, just 2 parameters, okay? What we want to do, so if we discretize this problem, we are going to have a linear system in this case, because this is an elliptic problem. That depends from a parameter setting. So that means for any pair of parameters, we should solve an high-dimensional linear system. What we want to do, we want to find a surrogate model. So something which is essentially, which can substitute the high-dimensional problem, and also well represents the parameter space. So now the questions. For sure, we have many questions. For instance, what does it mean represent? Why should we do that? So as I mentioned that, for instance, we want to frequently evaluate star. Or we want to, for instance, optimize with star. So this is something like shaped optimization. This problem also involves a frequent evaluation of the high-dimensional problem. So this is an example where what we want to do, we want to have a surrogate model, which is actually our goal. This surrogate model should be very cheap to be evaluated. So that's the idea of model order reduction. Replace a high-dimensional problem with a low-dimensional one, which is actually very cheap to evaluate. And if in case, as in this case, we want to evaluate many times, this is way cheaper than computing the high-dimensional problem. Of course, this might also be done for time-dependent problems. In time-dependent problems, we can also use more methods. But before going into details of model order reduction, I should go back and explain some finite differences method for a parabolic problem. In this So the problem that actually I have in mind that I want to solve is something like my dot t equal a y of t plus a function that depends on time y of t. T is in 0, capital T, and I have some given initial condition. So my problem is in RD, so that means that M and A are two matrices D by D, and F is a function from 0, capital T, times RD with values in RD. So let's suppose that we suppose that exists a unique Y that solves I'm going to call square this, that solves square. So actually this is a system of a simple system of ordinary differential equations. What I have in mind that D is very large. For instance, just to give an idea, this is something on the order 10 to the 4. So this is very expensive. And imagine that we want to approximate this problem. So imagine that we want to approximate this problem. What we need to do is to use, of course, an approximation scheme. And for instance, we can use an implicit scheme, an implicit Euler scheme, which is one of the easiest way to approximate this problem. So let's see what happens if we want to approximate this problem. If we want to approximate this problem with an implicit scheme. So first of all, we need to choose delta t time stepping. And a temporal grid. So we are going to define Ti equal I delta t, where T0 is 0 because our initial condition starts in 0. And Tm is equal to capital T, which is the end time. Then we suppose I actually going to use K as index, just to be consistent with the notation that I've used in the lecture notes. Okay, and then we suppose that Y of Tk can be approximated by Yk. So the solution at time Tk is approximated, so to say, well approximated by this vector Yk. Okay. Okay. If we want to approximate time derivatives, we can use finite difference. We can use forward finite differences or backward finite differences. For instance, so this is a notation to indicate the time derivative of y in a point that I'm going to call t hat. So if I use a Taylor expansion up to the first order, this is going to be y t hat plus delta t minus y of t hat over delta t. One can also use the backward approximation, which is y of t hat minus y t hat minus delta t over delta t. Both approximation, one can show that they are first order. And okay. So if we use this kind of approximation in our original problem square, what we are going to have, let us approximate using finite difference. In particular, we're using backward finite difference. Why we want to use backward finite differences? So our goal is to approximate partial differential equations, and in general, implicit schemes are more stable than explicit schemes. So in order to avoid the problem with the sort to say CFL conditions or to link delta x with delta t, I prefer to stick with the implicit scheme. With the implicit scheme. Okay. So if I want to use backward approximation, what I'm going to have is that I'm going to substitute the time derivative using this formula. So in our, what we are going to have is m yk plus 1 minus yk over delta t equal a yk plus 1 plus f tk plus 1 yk plus 1. This is for k from 0 up to n minus 1. And also for sure, we have that y0 is equal to y0. The idea is that yk tends to y of tk for delta t that goes to 0, so that we have convergence of the method. I'm not going to deal with the consistency, stability of the problem. I just want to recall to set our course. Okay, so if we have a closer look to this method, essentially when k is 0, so at the beginning this is given. So if k is given here, I want to compute y1. How it is defined y1? So again, I want to equal a yk plus 1 f tk plus 1 yk plus 1 y0. Okay, from here, what is the unknown? The unknown is yk plus 1. But here we have a problem because yk plus 1 is implicitly defined. So you see here that depends on f. So our problem essentially reads, and it's going to be something like m yk plus 1 minus yk minus delta t, which multiplies a yk plus 1 plus f tk plus 1 yk plus 1 equals 0. So this is actually our problem, which means to solve an implicit equation, How do we solve nonlinear equations? There is a huge literature. We can use Newton method. So how does it work? A Newton method. So here I define this problem as calligraphic f. So this is supposed to be a calligraphic f of x. This is going to be m x minus yk minus delta t times a x plus f t k plus 1 x. And this should be equal to 0. So once we set that f, this calligraphic f should be equal to 0, the unknown is x, so which is yk plus 1 in this case. Yk is given. To set the Newton methods, I assume that you guys are already familiar with the Newton method, as you should be, since you are following a course of numerical analysis here, based on numerical analysis. What we need to do here, we need to build the Jacobian of this function. What is the Jacobian in this case? Actually, the unknown part is x, so we compute the Jacobian with respect to x. So here we're going to have m minus delta t, which multiplies a, plus the Jacobian of the function f evaluated at point tk plus 1 x. So once you have f and the Jacobian, to make a Newton step, what we need to make use of Newton's method. We need an initial guess that I'm going to call this initial guess, sorry, xi, and to compute xi plus 1, we have these two steps. We compute the Jacobian of f in xi, delta I equal calligraphic f of xi, and then we update xi minus delta I. Okay, those are the two steps in the Newton method. But what you can see here, we need to solve a linear system dimension d by d. So the Jacobian provides a matrix. So this is a d by d matrix. And if d is very large, this linear system might be very expensive. Of course, we can exploit the structure of the Jacobian. It might be a sparse matrix, but still that might be expensive to solve. This is repeated. This is repeated at each this is repeated until convergence. This is repeated until convergence. For instance, one can use that xi plus 1 minus xi when they are very close. This could be the stopping criterion. All right. This could be the stopping criterion. All right. What could be a good initial guess? For instance, x0 might be yk. So that means the solution at the previous step. Okay, since what we want to find is yk plus 1, we can provide as initial guess the previous solution. Okay, the question now is how do we get a system like square? For instance, if we have a problem, something like y tilde t x of t, so that means that this is the time derivative equals some coefficient y tilde xx plus some nonlinear term, so f of t y tilde xt with xt in b times 0t. Then I also have y x0 equal some initial function, and then we also have some boundary condition that I'm using. Dirichlet boundary condition. So the unknown is for sure y tilde xt from b times 0 capital T with values in R. So this is the unknown part. With 0, y0 is given. Okay, and if I want to approximate this function in space, so this provides a semi-discretization, and the question is how the semi-discretization of this problem can provide a system in the form square. So let's see how it works. Again, we can use finite differences. We have already seen how to approximate the first order derivative, the time derivative. Here again, we need to choose a spatial step size, and we assume that xi is equal to a plus I minus 1 delta x for I equal 1 to n. So that means that I equals 0. I equals 0 means x0 equal a. I equal n. That means xn equal b. All right. If we need to see how approximate the second order derivative in the node xi t, this is going to be, I'm going to use the notation y xi t is going to be yi, Okay, so the index is going to be I. So here it is easy to show that it's going to be yi minus 1. This is y tilde time minus twice yit plus yi plus 1t over delta x squared. This is for e equal to up to n minus 1. So what we already know due to the boundary condition of the problem is that the y1 of t is equal to 0, yn of t is equal to 0. Okay, actually, what one can see from this approximation that we might approximate the second derivative using a compact notation, where A, the matrix A, is given by a 3-diagonal matrix, where we have -2 on the diagonal, and we have 1 in the upper diagonal and 1 in the lower diagonal. This is multiplied by 1 over delta x squared. For the nonlinear part, we can write f of t y of t equal small f, little f y t1 f t1 y. Not actually, we start from 2 because we already know the solution. We already know the solution at the initial point, at the boundary essentially. So this is going to be t y of t n minus 1. And our dimension of the problem is going to be d equal -2. So in this way, we are setting something like which I called the semi-discretization of the parabolic PDE plus f t y of t. Y of t0 is going to be y of 0, and the vector y of t, now this is a function from 0t with values in Rd, where each component is given by y2 of t up to yn minus 1 of t transpose. Okay, so to summarize today's lecture, first lecture, lecture 1. I have given motivation to use model reduction, especially for parameterized problems. Shape optimization problems. Then I have recalled quickly, very quickly, finite differences for ODEs and PDEs. In particular, we are interested in working a problem of this form. Plus initial conditions, where the dimension D is very large. And one can see equation square as a discretization, let's say a semi-discretization, of a parabolic PDE. This is actually more general, can be also done for a hyperbolic equation. Another good important point is that the use of implicit scheme to approximate this kind of problem, and the use of Newton method. Regarding the Newton method, there is a huge literature. Computation of the Jacobian might be very expensive, although it is sparse. There are thousands of methods that that improves this the standard Newton method. And for instance, one can be interested in the use of a method which is called Jacobian free Newton Krylov method. Well, essentially, one uses Krylov space to approximate the inner linear system that comes from the Newton method, and actually the Jacobian is never computed, or it's computed as a vectors, so to say. Okay, that's all for the first lecture, and then we will go for the second lecture. All right, thank you everybody, and if you have questions, just feel free to contact me.